Hi there. So in this section, we're going to be looking at polynomial functions and their graphs. At the top of the notes here, we start with the basic definition of a polynomial, and then just below that are several definitions associated with polynomial terms. By the time we end this section, you should be able to draw a rough sketch of a polynomial function based on the ideas and topics that are related to these terms and a few other definitions that we'll pick up along the way. Okay, so here at the top, you are given the basic definition of a polynomial, and it looks scary. It looks, just like I would say, quote unquote, in a very ugly form, but it's just the basic mathematical representation of a polynomial. This a sub n is just a coefficient. X to the nth power. A sub n minus 1, again, is just another coefficient. And then in the next term is raised x to the n minus 1. This just means that whenever, if you started with degree 5, then the next term would be 5 minus 1, so it would be to the 4th degree. And then the next term would be 5 minus 2, it would be to the 3rd degree, until you got to the very end where a sub 0 is just your constant. Over here to the right, I just made an example for you because I know that you've seen functions like this before and you recognize this. This is a polynomial, okay? It's degree 4 and it's going in descending order downward, right? This is x to the 4th, x cubed, x squared, x, then number, okay? That's all that this right here is talking about, okay? Now, just below that, we've got several definitions that we want to focus on. The polynomial that I'm going to use in terms of these definitions is the one that you see here. Let me highlight that for you. This is the one that we're going to be focusing on, this polynomial right here. And in reference to that polynomial, we'll now look at the first vocabulary term, and it's in reference to the degree of a term. The degree of a term is the sum of the exponents on the variables in that term. So if we look at our polynomial function here, we have x cubed plus x squared minus 3x plus 2. The degree of each term is just the sum of the exponents. So all of these just have, one variable term, so my exponent is just going to be one value. So the degree of that first term would just be 3. The degree of the second term would be 2. The degree of this term would be 1. The degree of any constant is always 0. It doesn't have an x. Remember, there's an imaginary 1 on that x, and this doesn't have an x at all, so its degree would be 0. Okay. Below that, we would reference now the degree of a polynomial, and the degree of the polynomial is, once you've found the degree of each term, the degree of the polynomial is the degree of the term with the highest degree. So for our example here then, our overall degree, comparing 3, 2, 1, 0, 3 is the highest, so we would say that this has an overall degree of 3, okay? Since that's the highest of your 4 terms that you see there. The leading term is the term with the highest degree. So typically what I'm going to recommend that you do is, if your polynomial is not given to you in descending order, so descending order just is according to your exponents, just counting downward. So like this one's x cubed, x squared, x, then no x's. Up here it was x to the 4th, x cubed, x squared, x, then no x's. So going in descending order. Once you've done that, then the leading term is that first term because it's going to have the highest exponent with it, okay? So here our leading term is x cubed. Just below that, we talk about the leading coefficient. That's just the number in front of that leading term. So in our case here, we've got an imaginary 1, so our leading coefficient here would be 1, okay? The constant term is just the standalone numerical value for your polynomial. If your polynomial is in descending order, then your constant term will be at the end. It is possible, though, not to have a constant term. In our example here, though, our constant term at the very end is 2, because it does not have an x associated with it. But if you had, for example, this polynomial here, y equals 2x squared minus 9x, it would not have a constant term because it doesn't have just a single number out here being added or subtracted, okay? All right, so let's move on down then to this box below where I've just given us several examples of polynomials from constant to quartic, and I want us to identify the degree, the leading term, leading coefficient, the constant term, and the y-intercept, okay? So this first one, you won't glean a lot of difference, and it'll in some ways you may not quite grasp it yet, but I think as we move forward with the table, you'll start to see the pattern. Now this first one, you have the function f of x equals 3. So remember, f of x is the same as y equals 3. And if you recall what that graph looks like, that means go to my y-axis up here at 3, and then I'm just going to be a horizontal line. So that's the graph, okay? The degree, remember, is associated with your variable. You don't have a variable here, so degree is 0. Leading term, though, that's all we have here is a 3, so my leading term is 3. The leading coefficient's the number, so that's also 3. The constant term happens to also be the same as the leading term in this case, which is another 3. To find your y-intercept, remember to find your y-intercept, you always let x equal 0 and you solve for y. Well, there's no x here to let equal 0. We already know that y equals 3, and sure enough, this graph is crossing the y-axis up here at 3. So 0, 3 is my y-intercept. All right. Let's go to the next one. I think you're going to start to see a little bit more on this one. All right, so this is a linear function, y equals mx plus b, so negative 2/3 x plus 4. I have, think about it in terms of your polynomial. It's first and then 0, in terms of like this is x to the first power and then this is no x's. The degree here, well, if this one has degree 1 and this one has, we'll do it down here, degree 1, degree 0, then my overall degree would be 1, because I take the highest. The leading term, it's already in descending order, so the leading term is that first term, and it's also the one with the highest power of x, so this would be negative 2/3 x. The leading coefficient then is just the number in front of that x, so that's negative 2/3. All of these pieces are going to be helpful as we move forward in graphing, so just so bear with me and just stay with me and see with you kind of see where this is all headed, okay? Your constant term, again, that's just the number at the very end if there is one. In our case here, we do have a 4. So now my y-intercept is 0. Plugging in 0 for x. Well, think about it. If you plug 0 in for x, the only thing you have left is that 4 at the end for your y-intercept, okay? You'll start to see a correlation between this constant term and your y-intercept, okay? All right, the quadratic just below that, negative 2x squared plus x minus 9. Let's think about the degree. First of all, find the degree of each term. So the degree of the first term, it has x squared, so that would be degree 2. Next term, degree 1. Constants always have a degree 0. So overall degree, pick the highest, that'd be degree 2. Leading term, it's in descending order, so leading term then would be that negative 2x squared. 2x squared. Leading coefficient, the number in front of that x squared, so a negative 2. The constant term, hopefully you agree, with the negative 9. And again, y-intercept, I'm plugging 0 in for x, so all of the first two terms are going to go away. The only thing I'm going to have left is that negative 9. So maybe even right here you're starting to see it. My constant term was 3, so was the y-intercept. Constant was 4, likewise for the y-intercept. Likewise for the next one. Constant term was negative 9, y-intercept was negative 9. That's always going to be the case here with these polynomials, okay? The next two, you'll notice for the cubic function, this is not in descending order. So if we write it in descending order, I have 7x cubed minus x squared plus x plus 1. And now if I evaluate my degrees of each term, then I have 3, 2, 1, 0. Overall degree then is the highest, be degree 3. Leading term, hopefully you agree, 7x cubed. Leading coefficient, number in front of that x cubed, which would be 7. Constant term, positive 1. And now we don't even need to say all this. We know the y-intercept then is going to be 0, 1. Last one is in descending order, x to the 4th, x cubed. Notice how it doesn't have an x squared, that's okay. And then it has x, and then it doesn't have a number out. We'll do our degrees. We have 4, 3, 1, just based on the exponents. So we say this is degree 4. Leading term, x to the 4th. Leading coefficient, the number in front of that x to the 4th, an imaginary 1. Constant term, you don't have one, so that's going to be 0. Y-intercept then would have to be 0, 0. Okay. All right, a little bit more to pick up before we can start getting into our graphing will be in behavior. In behavior tells you what your graph is doing as you go to negative and positive infinity. And it's based upon the degree. Excuse me. So in behavior, like I said, it depends on the degree of your polynomial. The degree of your polynomial has two options. It can either be even or it can be odd. If your degree is even, then you're going to have the same behavior, meaning your polynomial is either going to be both up or it's going to be both down. So up, up, or down, down, okay? I'll give you some more examples on the next page. Or your polynomial could be odd degree, and it will have opposite behavior, either up, down, so like this, up, then down, or down, then up. Those are your two options for odd degree, okay? We're going to expand upon this on the next page because we need to figure out, okay, well, there's a correlation between that leading term and whether you are both up or both down on an even, and likewise, there's a correlation between that leading term in terms of whether we go up, down, or down, up for that in behavior. So if you flip it on over to the next page, I thought I was. There we go. We have what's referred to as the leading term test, and it, like I said, it further explains the end behavior of a polynomial. If you have even degree and your leading term is positive, so you can have a leading term be positive or you can have a leading term be negative. So think about this. If you have a positive leading term and it's raised to an even power, then this just means that your graph is going to go up in both directions. It's going to be an up-up scenario. Perfect example that I think everybody can relate to. You remember our parent functions from the previous unit, y equals x squared. Think about what that graph looks like. My leading term here is positive, and it's raised to an even power, and we all know what the graph of y equals x squared looks like, right? It's this parabola pointing upward, and so we're saying that going to negative infinity, it's going up, and going to positive infinity, it's also going up. What the second scenario says, if you're also even degree, but your leading term is negative, so here you've got a negative raised to an even power, then that's the case where you are down, down as you go to negative and positive infinity. Perfect example here, I'll just stick with my x squared, but this time let's throw a negative in front. Y equals negative x squared. If you remember, as we talked about transformations, that negative just reflects me over the x-axis, and so sure enough, here's my graph, right? And I am, as I go to negative infinity for my x values, I'm going down. As I go to positive infinity for my x values, it's also going down. So this is what we mean by up, up, and down, down, okay? I think that the even degrees are the easier ones because they go in the same direction, and it's intuitive that if it's positive even, you go up, up. If it's negative even, you go down, down. Okay. Odd degree, you got to think about a little bit more. So if you're odd and positive, so odd and positive, then that means that your graph rises from left to right. So think of it this way: positive raised to an odd power. And so that means you rise from left to right. That means you start out going down and then you go up. So it's a case of down, up. I'm going to give you two examples. In your notes or in the solution key, I only gave you y equals x cubed. But I think even, let's go more basic than that. Let's just look at y equals x, right? Because we know what that graph looks like. The graph of the line y equals x, it doesn't have a y-intercept, so it's going through the point 0, 0. My slope is up 1 over 1, up 1 over 1. So here's my graph, and I am rising from left to right, right? It's a positive raised to an odd power, it's degree 1. So likewise, y equals x cubed, it's a positive raised to an odd power. But if you remember from your parent functions, x cubed still has to start out going down, and then it snakes up like that, okay? And I am rising from left to right. As I read this graph from left to right, I am increasing, okay? Scenario below that, well, if you're still an odd degree, but this time your leading term is negative, your graph is going to fall from left to right. So if you have a negative raised to an odd power, then we're doing just the opposite. We're going to start out up and end down. So this would be an up-down scenario. I'm going to use just the negations of these. So I'm going to use your y equals negative x for the first scenario, because you think about it, you know what that y-intercept there is 0, 0. And then from there, you're going to go down 1 over 1, down 1 over 1. So sure enough, as we read this graph from left to right, my graph is going to be falling. It's decreasing. And the next one, y equals negative x cubed. Think about what that negative does to this graph right here. It flips us over the x-axis. And so sure enough, here this would be my graph. And again, I am falling from left to right. All right. So we're going to put all of that together. It might help you to maybe write that somewhere and put it all on maybe one little note card for yourself, just so like you have it all in one spot. I think that would be helpful as you're trying to work through the problems. All right, so we'll move on down then to the next piece. They want us to identify the y-intercept and the leading term, and then determine the end behavior. Okay, so you'll notice here, I'm going to do example 1 with you and then let you pause the video and try example 2. Hopefully, if you kind of look here at example 1, you kind of notice that it is not in descending order. So that's the very first thing that I'm going to do to this problem is I'm going to put it in descending order. So let's rewrite f of x. So I've got this 5x to the 7th. Now I'm going to go minus 0.3x cubed, then x squared minus 2x squared minus x plus 15. Let's just find in order what they asked us. They asked us to find the y-intercept. So the y-intercept, remember, is plugging 0 in for x. So you think about it, if you plug 0 in for all of these x terms, they're going to go away, and the only thing you're going to have left is that constant term at the end, 15. So for these, you should be able to eyeball the y-intercept. Your leading term, if you take the time to put it in descending order, the leading term is the very first term, so 5x to the 7th here. Now, from that leading term, we can see that we have a positive value raised to odd or even. Hopefully you agree that that's an odd number. 7's odd. So I have a positive raised to an odd power. So then that means that I am rising from left to right, and I start out down up. Okay, so you can write the little arrows here, or you can do this. You can just say down up. Okay, that you on the left-hand side you're going to be going down, on the right-hand side you'd be going up. Okay, that's what we mean by end behavior. Okay, one more piece that we need to pick up, and then we're going to be ready to graph. Get a rough sketch, not a perfect graph yet, a rough sketch. These will, and by the way, for those of you going on to take calculus, you will use all of this extensively as you start doing in that course, so just a heads up. All right, so just below that you see a new terminology which is referred to as multiplicity. The multiplicity is used to determine if your graph crosses the x-axis or if it bounces off of the x-axis. I think your book uses the word touch. I like the word bounce because it kind of, when you look at the graphs, it kind of looks like it just bounces off of the x-axis, so like it hits it and comes back up, or hits it and goes back down, okay, whichever the case may be. Your multiplicity is based upon the exponent in each factor of your polynomial. So our exponent here, for example, would be k. So whether you cross or bounce is dependent upon, again, whether k is odd or even. There's a lot of rules here in terms of odds and evens and that sort of thing. So again, like I said, a little note card might be helpful just to kind of put it all in one place for yourself. So when k is odd, especially as you're studying and stuff like that. So when k is odd, when it's odd, that means that the graph is going to cross the x-axis at c0, because what would happen is we're going to find the 0 here. And when k is even, the graph bounces off of the x-axis at c. Okay. All right, so let's flip it over. On the top of the next page, we start practicing finding zeros and multiplicity. So I'm going to do number 3 and number 5 with you. Okay. Finding your zeros, we've done this before. Remember, is if it's already factored, then all that we need to do are to set the factors with variables in them equal to 0 and solve for x. So here, the 2 doesn't have an x with it, so I don't need to worry with that. But I have x plus 2 that would need to be solved, and I have x minus 3 that would need to be solved. The exponents are going to come into play when we start talking about multiplicity, which is then going to help us determine if we're crossing or bouncing. By now, hopefully you're getting really good at these, and you might can just eyeball it and say that this is x equals -2. I'll still show my work, though. I'll just subtract 2, so x equals -2 over here, add 3. So x equals positive 3. Remember, zeros are the same as x-intercepts, so this graph is going to cross the x-axis at negative 2 and positive 3. In some way, it might cross, it might bounce, but those are where you are points on the x-axis for us. Multiplicity are the exponents associated with those factors, so the negative 2 would have a multiplicity of 3. The 3 is going to have a multiplicity of an imaginary 1 there, okay? Since both of these multiplicities are odd, then that means at both of those zeros, I will actually end up crossing the x-axis. Okay. We'll illustrate this on a graph in just a moment, okay? But at the moment, I just want us to focus on, recall, how do you find zeros? Let's add in multiplicity and what's going to happen at those zeros, okay? Pause the video, try example 4, make sure you're tracking with me. And then I'm going to scoot on down here now to example 5, and I'm asking you to do the same thing. I'm going to find the zeros, multiplicity, and determine if you're going to cross or bounce. But the only difference is here, you'll notice that this function is not already in factored form, so we need to factor it. Because essentially you're setting this equal to 0, and you're trying to solve for x. So we need to factor this. The only way to multiply to give you x squared, x times x. The most common way to multiply to give you 15, hopefully you agree, 5 times 3. I want a positive 2 in the center, so on the outside I'm getting 3x, on the inside I'm getting 5x. I want a positive 2x in the center, so the only way to do that is to make my 3 negative, and then my 5 would be positive. So then if I set this one equal to 0, I'm going to get a 0 of negative 5. And if I set this one equal to 0, I'm going to get a 0 of positive 3. So I have two zeros at negative 5 and positive 3. Both of those factors have exponents up there of 1, so the multiplicity will be 1 for each of those. Since those multiplicities are odd, that also means that at both of those zeros, I'm just going to be crossing the x-axis. Let's draw a rough sketch of this one, because this one you kind of already have a little bit of knowledge base about it, okay? So again, just a little rough sketch here. So I have, I'm crossing the x-axis at negative 5, 2, 3, 4, 5. And I'm crossing the x-axis at positive 3, 1, 2, 3. Where's your y-intercept? Right, y-intercept, that's just your constant term. So I'm crossing the y-axis down here at negative 15. So let's do negative 3, negative 6, negative 9, negative 15. I'm just counting by threes on this scale. Negative 3, 6, 9. Oh, nope, negative 12, sorry. Negative 15. There we go. All right, so I'm crossing there. And leading term here is positive. So that means that this is a x squared, so it's a parabola facing upward. It's a positive raised to an even power, so I also expect my end behavior to be up, up. And so you should be able to generate a graph that looks something like that. It should have been more U-shaped, but you get the idea. I should have been crossing. There we go. Try to cross through that a little bit better. I did the first go around. Okay, so just that's where we're headed. We're going to we'll be a tad bit more precise. Okay. Another purpose of drawing my graph like this is to be able to illustrate the next couple of vocabulary terms. The next one is a turning point. We've talked about turning points before. It's a point on your graph where you change from increasing to decreasing, or vice versa, decreasing to increasing. So we can see down here, think of it as your maximum or your minimum. So like down here, I've got a minimum point. I change from decreasing to increasing, right? Next theorem down below says, well, if your polynomial function is of degree n, then it has at most n minus 1 turning points. So here we were degree 2, so what it's saying for us that I have at most 2 minus 1 turning point. And sure enough, we have just one turning point. We only have one spot where we change from decreasing to increasing, or vice versa. And then to work it backwards, it says, well, if your function has n turning points, here I have one turning point, then the degree of my polynomial f is at least n plus 1, 1 plus 1, it has to be at least degree 2. That's all that those next two theorems are stating for you. Just below that, how are we going to graph these by hand? We're going to be determining our n behavior using our leading term test. We'll find our zeros, determine our multiplicity, determine if we're going to cross or bounce at those points on the x-axis. We'll identify our y-intercept, And we'll make a table of values if we need to, but I really don't believe that we're going to have to, okay? A couple of other things to keep in mind. Polynomial graphs are always smooth and continuous. And what I mean by that is that when you say smooth, you shouldn't have any sharp corners like you do in an absolute value function, right? I should not have any hard V-shaped curves, okay? So I shouldn't have any sharp corners or sharp cusps in a polynomial function. And it should be continuous. There shouldn't be any gaps, holes, no asymptotes or anything like that. The graph just continues in some fashion, okay? All right, so if we flip it on over, last page, let's do that's number 6 and 7 together, okay? So as it tells you up here at the top that you are you're graphing by hand and you without the use of a calculator, and you're trying to determine your end behavior based on zero and also zeros, multiplicity, and your y-intercept. So let's first, it's in descending order, so let's first identify, let's get a different color here and make it smaller. All right, so let's first identify our leading term. In our case here, my leading term is negative x cubed. From that, we can see that this is a negative raised to an odd power. So it's a negative raised to an odd power, then I'm going to be falling from left to right, meaning I am up, then down, up, then down. Y-intercept would be fairly easy to crank out. Remember, you let x equal 0. Well, here, if I let x equal 0, I don't have anything left, so y would also equal 0. Then the next piece you want to find are your zeros. In our case here, it's not already factored, so we're going to have to factor it. So I would set negative x cubed minus 2x squared equals 0. And I factor out x squared. And actually, let's go ahead and factor out the negative. Let's factor out negative x squared. And then write what I have left over, so that would be x plus 2. And then now what would happen is we would set both of these equal to 0. So I would set negative x squared equal to 0 and x plus 2 equal to 0. And so this is, you divide by a negative, and so you have x squared equals 0. You're going to take the square root, so x equals 0. Over here, you're going to subtract 2. So x equals negative 2. So think about now your zeros, your multiplicity, and whether you're going to cross or bounce. So you've got a 0 at 0 and a 0 at negative 2. And then you go back to where, okay, with the 0, we got this from this term right here. It had an exponent of 2 on it, so the multiplicity there is 2. Because that's even, that means we are going to bounce. We're going to be bouncing at this 0. The next one, negative 2, came from right here. It has an exponent of 1, and that means we're going to be crossing at that 0. Okay. All right, let's plot some points now. I have a y-intercept at 0, 0. I have a 0 at 0, and I have a 0 at negative 2. Okay. From here, let's use our end behavior. Again, this is just a rough sketch. End behavior says that this graph has to start out going up, right? This is what my end behavior says. It starts out going up. Once I get to that 0, this is at negative 2, it tells me to cross, so I get to cross the x-axis. Then at some point I know I have to come back up and hit this other 0, but instead of crossing the x-axis at 0, you are bouncing and heading back down. Okay. Here's where the rough sketch comes into play. We don't know how far down, without using a calculator, and without putting in other values, we don't know how far down this goes. I mean, we could plug in negative 1, for example, and get a better value, but we're just doing a rough sketch. And over here, that's a good general representation. Okay. So this, like I said, this is just a rough sketch. Okay. All right, let's do another one. Down below in example 7. Nice thing about this one, it's already factored. in a factored form, but the leading term, we're going to have to do a little bit of work. But don't worry, you don't have to go through and FOIL and then multiply again. You don't have to worry about that. To find your leading term, when it's in a form like this, just take the first term in each parenthesis and raise it to the power. So the first term is going to be x to the second power. So you're going to have x squared. The next one's just going to be a plain old x. And the next one will just be a plain x. Now multiply all of that together, and that's going to leave you with x to the, remember when you multiply, you add your exponents. So x to the 2, 3, 4, x to the fourth power. So this is a positive leading term raised to an even power. So remember, even terms are always either up, up, or down, down. And because it's positive, it's going to be up, up. Okay. Let's find our y-intercept. Y-intercept doesn't fall out as nicely here, but it's still not hard work, right? You're still letting x equals 0, and you're solving for y, so we'll just do a little bit of work. But think about it. If you plug 0 in for all of these x's, then the first parenthesis just turns into 1 squared. The second parenthesis turns into -1. And then the last parenthesis, if you're plugging 0 in for x, is turning into -4. And then just multiply that together. So, we know 1 squared is just 1. 1 times -1, -1, -1 times -4, +4. Okay. So now we've got our y-intercept. Now lastly, we need to identify our zeros, the multiplicity, and whether we're going to cross or bounce. The nice thing about this problem, though, also, for this part, is that it's already in factored form. So if I take this first term, and if I were to set it equal to 0 and solve for x, I would have a 0 at -1. And the exponent on that is 2, so there's my multiplicity. Because that multiplicity is even, that means I'm going to bounce off the x-axis there. All right, let's move to the next term. If I set x minus 1 equal to 0 and solve for x, I'm going to get a, hopefully you agree, +1. An imaginary 1 on that exponent, so that's my multiplicity. And since that multiplicity is odd, it means we're going to cross the x-axis. And then lastly, that last term, if I set x minus 4 equal to 0 and solve for x, I should get a 0 at +4. Remember, these are all places where I'm going to cross the x-axis. And then it has an imaginary 1 up here as an exponent, so its multiplicity is 1. And because that's odd, it also means we're going to cross the full x-axis there. Okay, let's plot these points. You get to see a little bit better, I think, on this one. You have, I'll plot the y-intercept up here at 0, 4. Now let's plot, we've got zeros at -1, +1, and +4. So this one lets you see some good stuff here. Okay, so you'll notice that very first 0, that's the only one that we're going to bounce off of. And go back to your in behavior. In behavior says that as you are over here going to the left, then you should be starting from going up. So I am coming up, and then I'm going to bounce off the x-axis. You know you have to go through your y-intercept. Come through. Your next 0 is at +1. We already know that we have to cross the x-axis there. This is where we don't know how far down we're going to go, but we're just going to guesstimate here. And then come back up and cross through that last 0, which is 4. And notice how in behavior ended up at up, up. Okay. All right, I encourage you to look at example 8 now and try that one solo. And I think I've shown good work on the solution key. I'm trying to think if there's anything there. Probably the only thing different about number 8 is that whenever you do your leading term, it's very similar to what I just did here in example 7. Just don't forget you've got a -1/2 in front. So you're going to have a -1/2 in front of these pieces here, okay, as you work through this problem. But I think that the solution key will show you everything that you need there, okay? All right, well, let me know if you need anything, and thanks a lot. Bye.